Hey guys, in this video, we're going to go over the goodness of fit tests. But before we go over the goodness of fit tests, let's talk about the chi-square distribution. The chi-square distribution is a distribution we use to model certain situation in statistics. For example, like the goodness of fit tests, tests of independence, and tests of homogeneity, all three use the chi-square distribution. The chi-square distribution, the curve is non-symmetrical and is skewed to the right. There is different chi-squared curves for each degree of freedom. So if you look at the drawing or the graph here, each of these colored curve corresponds to different degrees of freedom. One thing you'll notice is that the higher the degrees of freedom, the more the shape of the curve looks like a normal distribution. It's still curved to the right or skewed to the right rather, but the higher the degrees of freedom, the shape looks more and more like a normal distribution. And the last thing is that the test statistics for any test is always greater than or equal to zero. So you have all these test statistics, they're either zero or they're positive. All right. So now, what is the goodness of fit tests? In this type of hypothesis test, you determine whether the data fits a particular distribution or not. So this table here pretty much provides you with all the information you need to answer the questions on your homework. Obviously, you're going to also have to rely on prior knowledge that we learned in hypothesis tests, such as when to reject the null and when to fail to reject the null and whatnot. All right. Another thing I wanted to note is if you have a TI-83 plus, you have to use this method to find the test statistic and the p-value. But if you have the TI-84 plus, you don't need to do it this way. You could do it this way. However, there's a function that would give you the test statistic and the p-value, and that function is chi-square golf test. All right, so let's go ahead and jump right into a problem. See what we have here. So when you're on Canvas, you want to go to assignments and then 11-2 or 11.2. Let's go ahead and look at two problems, question 1 and question 2. So question 1 here says, Acme Toy Company prints baseball cards. The company claims that 30% of the cards are rookies, 60% are veterans, and 10% are all-stars. Suppose a random sample has the following cards. Test Acme's claim that the distribution is a good fit with the prints of baseball cards at an alpha equals 0.05 level of significance. Okay, so what we have here is these are the observed frequency for the number of rookie cards, veteran cards, and all-star cards. But the expected frequency is, according to the company, is that 30% is rookies, 60% are veterans, 10% are all-stars. So what you want to do here is you want to figure out what those expected values are, those expected frequencies. Well, the way you would do this is you would look at the total number of cards. So here we have 30 rookie cards plus the 100 veterans card plus 20 all-star cards. So there's 150 cards. The expected frequency for these 150 cards is that 30% of them are rookies. So what we would do for the expected frequency for the rookies, we take the 150 and then multiply it by 0.3. Again, 0.3 is the decimal equivalent of 30%. So the expected frequency for the rookies should be 45. Likewise, for the veterans, well, the veterans is 60% are veterans. So that's So we're going to take the total 150 and then multiply it by 60% or 0.6, which is the decimal equivalent of 60%. So 90 of the cards, of the 150 cards should be, is what we expect to be veteran cards. And then finally for the All-Star, 10% should be All-Star. So we would take the 150 and then multiply by 0.1, which is the equivalent of 10% as a decimal. So 15 would be the expected frequency for the All-Stars. These are what we observe. These are the expected frequency according to the company. And we want to see if there's a goodness of fit, if the observe fits what we expect. Now, obviously here, they're not the same. However, is it significantly different? That's what we're trying to figure out, right? So question B here says, what is the chi-square test statistic? And then what are the degrees of freedom? What is the p-value? And then you make the comparison of the p-value compared to alpha. All right, to get the test statistic and the p-value, we're going to use a function. Actually, I'm going to do it both ways. So let me go back here. I'm going to do it this way and then do it this way. First things first, what you need to do is you need to input this into two lists. Input the observed frequencies in list 1, then expected frequency into list 2. So let's go ahead and do that. So we're going to do that by going to stat, edit. So we have 30, 100, and then 20, right? And then the list 2 is our expected frequencies. That's 45, 90, 15. Okay. So with the first method, again, this method you're required to use for if you have the TI 83 plus. You would do the following. You would go, so we already inputted the observed values in list 1 and the expected values in list 2. In L3, we're going to define L3. So go up to L3 and then press enter. We're going to define it as L1 minus L2 raised to the second power and then divided by L2. So that is what we want to input. L1 subtract L2 raised to the second power, making sure you put parentheses around L1 minus L2, and then dividing by L2. And that's going to create a third list. And to get the test statistic, we're going to run one var stats on that third list that we created. So I'm going to go to stat, calc, one var stats, and I'm going to run it on L3. And the test statistic is the sum of the x's, which is right here, 7.77. So it says round to 3 decimal places. So 7.778. 7.778. The degrees of freedom, if you look back at the notes, the degrees of freedom is a number, is n minus 1, where n is a number of categories. So in this case, there's 3 categories. There's these 3 categories. So the degrees of freedom would be 3 subtract 1, which is 2. For the p-value, the way we're going to find the p-value is we're going to use a function called chi-squared CDF. Take note of the test statistic as well. We're going to need that. So the test statistics we found was 7.778. So we're going to get to the chi-square CDF, we're going to press second R's, and then it's function number 8. So the lower is our test statistic, 7.778. The upper, we're always shading to the right. So if you imagine the chi-square distribution, we would have the lower be the test statistic and the upper, and it shades to the right. So the upper is positive infinity, but we're going to use quadruple 9 as our proxy. The degrees of freedom, again, is 2. And we're going to press paste, press enter. And there's our p-value. Rounded to 4 decimal places, that's going to be 0.0205, right? 0.0205. All right. Now, that is this method of figuring out the test statistic and the p-value for the goodness of fit test. We're going to also use the chi-square golf test, which is only available on the TI-84 Plus. So if you have the TI-83 Plus, unfortunately, you cannot use this. You don't have this function. Okay, so what you do here is you input the observed values in L1 and then the expected values in L2. You don't need that third column or that third list if you're using chi-square golf tests. All right. So let's go to chi-square golf test because we've already inputted in list 1 and list 2. So we're going to press stat. We're going to go to tests and L1, L2 looks good for the observed and the expected frequencies. Degrees of freedom is 2. That's correct. We're going to calculate. And automatically that gives us the chi-squared test statistic and the p-value. So with the chi-square golf test, with that function, it's a lot easier. But again, if you have the TI-83 Plus, you don't have that function, you will need to use the first method, right? But with chi-square golf test, it just automatically gives you the test statistic and the p-value. All right. I'll let you guys do the comparison of the p-value and alpha. One thing I forgot to mention is when the null hypothesis for goodness of fit tests, it's always a statement that the observed data conforms to the expected distribution. So the observed data conforms, meaning like it's not different, not so much different than the expected distribution. Where the alternative is a statement that the observed data does not conform to the expected distribution. So if we were taking this as an example to that, the null hypothesis would mean that the observed frequency conforms to what the company claims with their distribution of playing cards or baseball cards. All right. And then the alternative would be that it does not conform. The observed does not fit with the expected. That's what the alternative would suggest. All right. So once you have all this inputted, what you want to do is submit the question, right? I'm just going to go ahead and go to question 2. Obviously, I didn't finish it all, but I'm going to go ahead and go to the next one, the next question. So question 2, it says, perform a goodness of fit chi-square hypothesis test, where alpha is equal to 0.05, for the claim that all outcomes of rolling a 6-sided die are equally likely. You roll a die 93 times and observe the below frequencies of each result. Enter the expected frequencies. So enter the expected frequencies here. These were the observed frequencies. So for example, like rolling a 1 19 times, we rolled a 1 19 times, right? This is the observe. And what do we expect? Well, it says that the claim is that all outcomes of the 6-sided die are equally likely. So what you need to do is you take the total and you would just divide it among the 6 numbers, right? If it's equally likely, if I rolled it 93 times, then all of these should be the same. All of these should be the same. I should get the same amount. So the way you would figure that out is you would take a couple of ways. You can add up all these, but all of this adds up to 93 because there's you rolled it 93 times. But you would take the 93 and then divide it by 6. Why 6? Because there's 6 different numbers, 6-sided die. All of them should be equal. If you roll it 93 times, each of these should be, you should get each of the sides 15.5 times. Now, obviously, that is, you can't get 15.5 because, that's not a whole number, but it is what it is. That's the number that we got with 93 divided by 6. All right, so whenever it says equally likely or um, equal distribution or same distribution, then what you're doing is you're just taking the total number of frequencies from the observed and then divide it among the categories. So in this case, the categories are the numbers on the six-sided die. All right, that's what your expected frequency is. And now it's asking for the chi-square test statistic, critical value, which I'll show you in a bit, the p-value. So I'm just going to use the chi-square golf test. If you need to refer to, you can always rewind if you don't have the TI-84 and you need to do it the other way. But just to speed things up, I'm going to use chi-square golf test. Oh, I forgot to input the observed and the expected. So the observed are these numbers, and the expected is all 15.5 because we're expecting all of them to be the same. Okay, 15.5. All right, and then we're going to run chi-square golf tests. Excuse me, I'm recovering from a cold. All right, degrees of freedom. Well, there's 5 categories. I'm sorry, 6 categories. So degrees of freedom is 6 minus 1, which is 5. And we're going to calculate. There's our test statistic. There's our p-value. So the test statistic is rounding to 4 decimal places is 9.6452. 9.6452. And then the p-value is 0.0859. All right. Now, what about the critical values? There's a link here to the chi-square critical value calculator. You can use that if you like, but also get comfortable with using the table because on the tests, if it's in person paper tests, you're going to need to know how to use the table. So I have the table right here, the chi-square critical value table. If you're on Canvas, if you're working from, you're working on your home, the homework from home, you can access it by going to Files and then going to Critical Value Tables. And then there's the table, chi-square critical value table. All right. Okay. So here, let's go back to our table here. Okay. So what we need is the area to the right, which is what alpha is, and then the degrees of freedom. Well, for the problem here, the degrees of freedom is 5, right? Because it's 6 minus 1, which is 5. And alpha is 0.05. So we're in this column, and degrees of freedom is right there. So the intersection of that row and column is 11.071. It says round to 4 decimal places, but this only goes to 3, so that's fine. Just putting this down would be fine. And then you make the comparison of the p-value. So p-value is, so this is the p-value is greater than alpha, which means we failed to reject the null. And I'll let you guys make this conclusion yourself. But just remember that the null and the alternative, the null is the statement that the observed conforms to the expected distribution, and the alternative is that the observed does not conform to the expected. Okay, so that's it for this section. As always, if you have any questions, please reach out.